In this section, we're going to talk about the variance or standard deviation of a random variable. So we often want to measure the spread. Okay, so this is all about spread or variability of values taken by a random number. So the variance of a random variable is defined to be, so the variance of x is the expected value of x minus the expected value of x squared. So that's kind of interesting. So you already find the expected value once, do x minus that, and then you find the expected value again, in a way. Or, and this one is usually easier to compute, you can find the expected value of x squared minus the expected value of x all squared. So we find the expected value first and then square the entire thing. A few notes: the variance will always be positive, because notice everything up here is kind of getting squared. The variance measures the spread of our distribution about the mean value. Now mean is another word again for average. And larger values of variance mean that our distribution is more spread out. Let's see, and if you want to find standard deviation, you take the square root of the variance. So standard deviation of x is the square root of the variance of x. Now there's a few alternative symbols we're going to use. So mean, or expected value, or average, is this little mu. This is the Greek letter mu. That's how you say it. Okay. Variance is this little sigma squared. So again, this is Greek for sigma. Okay. And standard deviation in the square root of sigma squared would just be sigma. So there's some formulas you can use for the variance. We wrote it up there, but here's actually what you'll end up doing. Is if you have a discrete random variable, you have to use the first one with the summation. And you take each x value minus the mean, or the average, squared times each probability. If it's continuous, you'll use the integral instead, and it'll be x minus the average squared times the PDF. Now, just so you can kind of understand what we mean about spread out, here's two different examples. In this first example, our graphs seem like they're the same shape, but they're shifted. And so in this one, here would be the mean of this graph, and here's the mean of this graph. And so they have different means. One is shifted up quite a bit, so different means or averages. But notice it's the same shape, or they're spread out the same, so that means it's the same spread or same variance. But in this one, notice they both seem to be centered about the same place, so they have the same mean. Remember, for a symmetric distribution, we know that the mean, or the expected value, is just right there in the middle. But on this one, notice we kind of have, this first one is kind of skinny, but the second one is a bit fatter, and so this one is more spread out. Okay. So this one has a bigger variance. So they have different variances. So again, the one that's kind of fatter or more spread out, it's kind of squished out further, is the one with the bigger variance. And then hence standard deviation as well, because variance and standard deviation are just the square root and square of each other. So how do you actually put this into practice? How do you find it? In this example, from past experience, Linda knows the probability distribution for her car sales per day. Let's find the standard deviation of the number of cars she sells. Okay, so in here she has each car, the number of cars sold, and the probability. The first thing you want to do, even though I didn't say, is you have to find the average, because before you can find standard deviation or variance, you have to find average. So let's find the average, or the mean, or the expected value. And this seems to be discrete, so we'll use our summation. We'll sum up each x value times its probability. So the first x value is 0, its probability is 0.3. Our next x value is 1, its probability is 0.4. And then we have an x of 2, and its probability of 0.2. X is 3, its probability is 0.1. So this gives me 1.1. So the average is 1.1 cars per day. First step is always find the average, because now you can go through and actually try and find the variance. So to find the variance, you have to do each xi value minus the mean squared and times by its probability. So what this is going to look like is my first x value is 0. I minus the mean or the average of 1.1, square it, and times it by its probability of 0.3. And this is 0.363. And I have to do this for each one. Notice this takes a long time for discrete random variables. So my next x value is 1 minus the average of 1.1 squared times by its probability of 0.4, which is 0.004. Then we have our new x of 2 minus the average of 1.1 squared times its probability of 0.2, so 0.162. And 3 minus 1.1 squared times 0.1 gives me 0.361. Okay, now that we've done all the preliminary work, we can actually find the variance. So the variance of x, or sigma squared if you prefer, is equal to the summation. We said we're going to take each xi value minus the mean, square it, times it by the probability. So we found each of these x minus the mean times the squared times the probability. Now we just add them all up. So 0.363 plus 0.004 plus 0.162 plus 0.361 equals 0.89. Now technically, if you went through and followed your units, this was cars minus the average car squared times the probability. So this is actually cars squared. Now if you think about that, it doesn't really make sense to have your starting units squared. Like dollar squared doesn't make sense, car squared doesn't make sense. And that's one reason I think that they came up with standard deviation. So they said find the standard deviation. That was my final goal. Standard deviation is sigma, or just the square root of sigma squared. That's easy to remember, right? So the square root of 0.89 is 0.943, and if you take the square root of car squared, you get back to cars, which is a unit that actually makes sense. So my final standard deviation is 0.943 cars. Now standard deviation to us doesn't usually mean as much. People will ask, okay, well what does 0.943 mean? It doesn't really mean that much to me unless I try and compare it to someone else and I can see who has the higher standard deviation. And a higher standard deviation means you're more spread out. So that would just mean they have more variability. Our next example, once again, we're talking about the same judge. He hears cases. The length in years has this distribution. F of x is 1/9 x squared. X goes from 0 to 3. Notice this is continuous. So we're going to do things for continuous functions. And in our previous example, we found that our mean is equal to the expected value of x, or 2.25. Now, if you forgot how we did that, the expected value of x for continuous is you just integrate f times f of x dx. So we would have integrated from 0 to 3 of 1/9 x squared dx, and you get 2.25. Because before you can find variance, you always have to find the average. But now the variance of x, because these are x, sorry, I just started looking at the wrong one, or if you prefer, sigma squared, is just going to always be equal to the integral of x minus the mean squared times the PDF of x. Okay, so in our case, again, we only care about it from 0 to 3. We're going to have x minus our mean, which is 2.25, squared times little f of x, which is 1/9 x squared dx. And this, as long as I look at the right thing, is 0.3375. So we found the variance of the length of the sentences. Now our second judge, this is what I started copying down, has 3/16 square root of y from 0 to 4. So again, first step, you always have to go through, find the expected value. So the expected value of x, or mu if you prefer, is equal to the integral of x times f of x dx. Okay, so we're going to take the integral from 0 to 4. Now, instead of x's, we're talking about y's, so let's just go through and replace all these with y's. Doesn't really make a big difference, it's just a different variable. Okay, so from 0 to 4 of y times 3/16 square root of y dy. And this is 2.4, so that's the average for this judge. Let's find the standard deviation. So before we can find standard deviation, we find the variance. So the variance is equal to the integral of y minus the mean squared times the PDF of y. So in our case, we'll integrate from 0 to 4 of y minus our average, which is 2.4, squared times 3/16 square root of y dy, which equals 1.097. And so the standard deviation is the square root of that. Square root of 1.097 equals 1.047. So that's our standard deviation. Now, do you remember how I wrote down two formulas originally? So there are two different formulas. So the second formula is the variance of y equals the expected value of y squared minus, and then you take the expected value of y and square it. So the expected value of y, we found that up above, but humor me, let's go ahead and write it here, is you take the integral of y times f of y dy, or we integrated from 0 to 4 of y times 3/16 times square root of y dy, which is 2.4. Now, so that was expected value of y, and we'll have to square it. But now expected value of y squared, we haven't actually found anything quite like that. But if you remember when we first talked about expected value, we said if you want the expected value of something like y squared, instead of putting a y, we just put a y squared. So it's actually really simple. Whatever you want to take the expected value of, that's just what you put here in your integral and times it by the PDF. So we'll integrate from 0 to 4 of y squared times 3/16 square root of y dy. And this is 6.85. So now we want to find the variance of y. And so it's just going to be the expected value of y squared minus the expected value of y all squared. So in our case, the expected value of y squared is 6.85 minus the expected value of 2.4 squared, which is 1.09. So depending on which way you want it, this one up here really wasn't that hard to compute because it's a pretty simple integral. Sometimes though you get really hard integrals, and this actually ends up being easier and something that we can compute.